Thank you, Amber. So, as a friend and colleague, it's my pleasure to introduce such a great professor like him. If I tell all his career and achievements, it will take like more than an hour. So let me summarize something else. So, as I know, like 65% of the people around the world love his works because all of them has a low back pain problem. So, so it's a good deal for the 65% around the world. So Dr. Zelik received his bachelor's degree and master's degrees in biomedical engineering from Washington University, and then his PhD in mechanical engineering from University of Michigan. And he is an engineering professor at the Vanderbilt University, specializing in his biomechanics, prosthetic, exoskeleton, exosuits, and smart clothing and wearables. So he also co-directs the Center of the Rehabilitation Engineering and Assistive Technology in Vanderbilt University. And also he's co-founder and chief scientific officer of Heroware, which is a wearable tech company that makes back assist suits to support workers in physical demanding jobs. And also, this is my personal opinion, but he also used social media very effective with the sharing scientific knowledge, which is very good fun. So I'm really, and we're really happy to have you here right now. So now stage is yours. Thank you.
Awesome. Well, thanks for the introduction. Thanks everybody for being here this afternoon. I'm excited to just spend some time with you all. I'm going to be talking about wearable assistive tech, talking about sweaty, squishy, quirky humans. The title is not too formal. I am not too formal. So if you have questions along the way, feel free to chime in, or happy to talk about anything you like at the end. All right, it was mentioned at the beginning, just want to disclose I have two affiliations. I basically wear two hats. One is an engineering professor at Vanderbilt, and one is this chief scientific officer and co-founder at Heroware. Today I'm really going to be talking about interdisciplinary and translational research, and so both of these play a role in kind of my perspective and my approach to that research and development. First, a little bit about myself. So I grew up in Pittsburgh, Pennsylvania. One of four boys in my family. I was always very physically active. I was fairly reckless with my body. I broke quite a few bones, got quite a few stitches. And I like to think as a kid, I was always testing the limits of the human body. I was fortunate in college to discover biomedical engineering, which was a much safer and more academic way to test the limits of the human body. When I started as an undergrad getting into research, I was more working in the cardiac bioelectricity realm. And so the first thing I did right after undergrad was go work for a short time with a medical device company. So working on implantable pacemakers and defibrillators. I ended up going back to grad school at University of Michigan, and this is where I discovered the field of biomechanics, of prosthetics, of assistive technology, and became pretty smitten by it. I just really liked the mission of trying to improve health and mobility for folks with disabilities, and like the challenge of figuring out how to use engineering principles and science to advance that means. After graduate school, I went over to Europe. I lived in Italy for 2 years and did a postdoc there, focused mostly on neuromotor control. And then in 2014, I came back to the US and joined the engineering faculty at Vanderbilt, helped set up this CREATE, Center for Rehabilitation Engineering and Assistive Technology. And in a nutshell, our mission is to try to restore health and mobility and independence to folks with physical disabilities through advances in science and technology, or to try to prevent these injuries or disabilities from happening in the first place. I describe this as 90% trying to reduce disability in society, and 10% not so secretly trying to turn ourselves into superheroes. So today, I just want to talk about two main categories of things. One was our approach to innovation and translation of research and development. And then the other were just some lessons I've learned along the way, trying to develop tech that people actually want to wear, with an emphasis on the word actually, because it turns out it's really easy to make things that people don't want to wear, but to create things that are both assistive and effective and helpful, but also in a form factor and in a technology solution that can fit into people's lives. So first up, a little bit about how we approach innovation. Vanderbilt is located in Nashville. We are located as a university directly next to the Vanderbilt University Medical Center. So our group, our Create Center, is in an engineering and science building that is just across the street from the Veterans Affairs Hospital, about a 2-minute walk away, and about a 3-minute walk to the Vanderbilt University Medical Center. So we really benefit from the proximity of being close to patients, of being close to doctors. I'm an engineer by training, so anytime we're working with devices or research that's focused on trying to improve clinical care, we always have a clinical collaborator. Might be somebody that's focused on care for individuals with limb loss or orthopedics or spinal cord injury or low back pain. But I think that's been part of the infrastructure and part of the collaboration that's really helped us steer our research and hopefully make sure we're working on scientific questions and engineering questions that are relevant to patients and practitioners. Just a little bit more about the center. So we have 3 different engineering labs within Create. Personally, I come a little bit more from the human biomechanics side of things. My research spans from theoretical to applied, but I'd say I'm a little bit more on the applied side in what I do. Long before I arrived to Vanderbilt, and one of the reasons I came to Vanderbilt is because Michael Goldfarb has been here for about 25 years now. He is one of the foremost experts in the world on wearable robotic technologies, exoskeletons, prosthetic limbs. And so he comes more from the robotic side, again, with a little bit of a slant towards the applied research. And we have a third member, David Brown, who's a fantastic roboticist and controls engineer, who comes a little more from the theoretical side. And so we each bring a different flavor, a different perspective. We have enough overlap to collaborate well together, but not so much that we're really stepping on each other's toes. And so it makes for a fun environment to collaborate both within different engineering disciplines, across different science disciplines, and of course with the clinicians who are next door. So in terms of physical setup, we have co-located facilities. We have 3 different engineering labs, where we do mechanical fabrication, electrical fabrication, computers for data analysis. And immediately adjacent to that is a 3,000 square foot motion analysis lab. So this is a room that's surrounded with motion tracking cameras, force sensing plates in the floor, a force instrumented treadmill, muscle activity sensors, and a lot of other stairs and ramps, and basically just a flexible, versatile space where we can test everything from robotic exoskeletons to passive prosthetic limbs to individuals running or lifting or doing whatever physical task we're interested in exploring. And then also some of our more recent work over the last few years has gotten more into smart clothing and exosuits. And so we also have some soft goods fabrication capabilities, sewing machines, and we have a apparel designer on staff as well that helps with some of these aspects of the research. So in terms of the research itself, we spent a lot of time trying to understand the science of human movement called biomechanics using these different instruments we have in the laboratory. We use musculoskeletal and biomechanical modeling to understand how people are moving as they move and perform different tasks, how much load is being put on different parts of their body, how much torque they're generating about different joints. It's occurring to me now, this video seems completely normal to me, but I suppose to most people, seeing a bunch of skeletons with their heads cut off, lifting and leaning might be a little bit strange, but we enjoy this nonetheless. We then take our biomechanical understanding and use that to motivate the design of devices. So these could be robotic prosthetic limbs like the ankle shown at the top or the robotic knee and ankle shown on the right. Or they could be purely passive devices. So we may be trying to understand lower cost solutions or just how specific parameters, specific aspects of the design affect how individuals with limb loss move and navigate their world. We work on exoskeletons for people with physical disabilities, could be spinal cord injury or someone after they've had a stroke. And we also work on technologies such as wearable sensing technologies or wearable assistive exosuits, which are really intended for people who are already healthy, who are perhaps working in physically demanding jobs, and we want to keep them healthy and we want to keep them safe. And then we spent a lot of time going back and forth between this assessment lab and the engineering lab, you know, on the engineering side, we think we have a clever idea, we build it or we design it, we go over to the human motion lab and realize we maybe weren't as clever as we thought. Once we get patients in and have them test it out, we learn from their feedback, and it's very iterative and very entwined in terms of, you know, learning what we don't know, trying to figure out what some of the key challenges are for these individuals, such as walking on uneven terrain, and then using that to inform our mechanical design or our control strategies for devices that we hope can be more enabling for these individuals. We also, you know, build custom apparatus to try to understand, you know, the bounds of current technology. This is a really interesting one where it kind of looks terrible at face value. We bring in individuals with above knee amputation, and we create this special platform where we can trip them. But the idea is to really understand what puts them at risk for falling. This is a group that is at 200 times, they're 200 times more likely to trip and fall than their age-matched healthy counterpart. And so what we want to do is understand how they typically try to recover with their current prostheses, and then use that to inform how to build next generation prosthetic knees that have human-like reflexes and can help them maintain their balance. Some of the work we do is with purely wearable systems or products, and some of it is research. We use emulator systems. So these black cabinets are actually robots with bike brake cables that connect out to prosthetic limbs. And we can use this to explore different behaviors or different control strategies in the laboratory to help inform the device design. And then once we understand what we're designing for, then go and actually create the wearable technology. And we're not limited to the lab. We also take some of our technologies out whenever they're ready, and we test them out in the field. This is an example of a warehouse worker where we were testing an early version of our exosuits to make sure that it could relieve strain on their back while they were lifting and leaning, but also allow them to do other aspects of their job, like hop in a forklift and drive around to do the work that they needed to do. We do some collaboration and have some engagement with the military, the Army in particular. Fort Campbell is located an hour north of us. And you know, we're looking at ways to leverage some of the capabilities that we have at Vanderbilt, some of the research we do to help the soldiers, in this case, to try to reduce some of the burden on these soldiers who are at risk of back pain and back injury and overexertion injuries. On the right is a former grad student of mine and one of the co-founders of Heroware, basically hopping in line with the soldiers and grabbing a 50-pound howitzer round. So not just trying to understand the science behind these different tasks, but really what are some of the physical demands and the best we can, putting ourselves in those situations so we can design solutions and design research that is translatable and realistic and relevant. Within our center and within Vanderbilt, we also try to translate technologies outside the lab. So when we do advance things to the point where we think there's a potential benefit to society, the flagship example is really the Parker Indigo exoskeleton. This was developed before I even got to Vanderbilt. So Michael Goldfarb and his team developed this robotic exoskeleton on the left that allows people who are paralyzed from the waist down to actually stand up and walk. This was licensed to a robotics company called Parker Hannafin and has since been turned into an FDA-approved product for paralyzed individuals to use either in the clinic or at home. Heroware is a spin-off company out of my lab that created this back assist exosuit. It's essentially a 3-pound suit that takes over 50 pounds of strain off your back each time you bend or lift. And so this is for folks who do a lot of physically demanding work in warehouses or logistics, construction, agriculture, those types of jobs. And Synchromotion is another example of an early stage spin-off company out of our center that is creating a new type of robotic prosthetic ankle to try to help improve mobility and livelihood for people with limb loss. You know, within our center, we take a lot of pride in trying to train the next generation of engineers and scientists and innovators, so folks that are working in this very interdisciplinary space. And we're very thankful for different funding mechanisms that allow us to do the work that we do. I'll just end this kind of section with a couple of pictures that are kind of near and dear to my heart. You know, the environment we work in, especially pre-COVID, so this was back in January of 2020, you know, being in meetings where we have a clinician whose office is, you know, 10 minutes walk away on the Vanderbilt Medical Center campus, interacting with an undergraduate, a postdoc, and a grad student. These are the kind of interactions we try to foster. It was also really cool back same month, January 2020, to walk into my engineering lab and see 7 really talented females working together on different projects. Engineering continues to be a discipline where we're severely underrepresented in terms of females. Mechanical engineering, for instance, only about 14% of the PhD students each year are female. And so creating an environment that is inclusive and where we can bring in as many diverse, talented folks as possible, and especially build up underrepresented groups like females is something that's also, again, near and dear to us and core to our mission. Okay, let's switch gears and I'll talk a little bit more about the research itself and some lessons learned in trying to develop wearable tech that people actually want to wear. So here are the lessons I'm going to focus on. I prefer to just kind of share them up front. The first one that I'm going to talk about is just beware of too little science, but also too much. The second is to frequently reassess your questions and priorities. And the third is, if you're designing for humans, then just remember they're sweaty, squishy, quirky, and multifaceted. Okay, so the first lesson, beware of too little or too much science. And a lot of these lessons, I prefer to just share through kind of the organic stories of the research. So rather than just the methods and the results or what we found, I'll kind of, I guess, indulge me and I'll kind of tell the story behind some of this research. And this first one started back around 2016 or 2017. And this orthopedic doctor named Leon Scott had approached our research group asking what I thought was a pretty simple question. And at the time, he basically said, look, I run this sports medicine clinic, and every week I have runners coming into my clinic and they have these stress fractures. And the only thing I can do to them once they've developed a stress fracture is just tell them not to run for the next 2 or 3 months. And they're miserable. And every week, this is, the most common patient I see. Is there any way that I could use some kind of wearable sensor and use the information it gleans to just alert these people that they're putting themselves at risk for these stress fractures before they happen? And stress fractures are overuse injuries. So basically repetitive loading to your bones causes an accumulation of micro damage. And if that rate of micro damage outpaces the rate at which your body can heal itself, then you develop these stress fractures and have to wait for them to heal over the course of months. And so I just thought this was a great question because it seemed like the kind of thing we should be able to answer with biomechanical science. And at first I was, very confident. Oh yeah, of course we can do this. As I thought more about it, I thought, okay, maybe we can do this. And at the end I said, okay, I'm not really sure what we can do, but this is super interesting. So let's just start meeting up and learning more about it. Initially, it was just myself and Dr. Scott, but a couple of my students got wind of it, and we started meeting up informally and just having these little journal clubs where people would share what they read, something interesting they found. It started focused mostly on the scientific literature, but then we also quickly pivoted into, current state-of-the-art wearables. What's on the market? What are people using? And there were a number of wearable sensor technologies that were business to consumer type of products. I mean, you could go online and buy them, little pods or boxes that you would put on your shoe or on your shank. And typically they contained inertial measurement units. So they'd be accelerometers or gyroscopes. And essentially what these devices did is they measure how hard your foot hits the ground. That's mostly what they're picking up with these accelerometer sensors. And a number of them had injury risk metrics or injury risk algorithms that were reporting back to runners and telling them something about their risk of injury. And the general thought process kind of went as follows. And this is a plot of the force underneath your foot over the stance phase of walking. So if you were to come into our lab and run across one of our force plates, you would generally see this kind of peak. And there'd be this little impact peak that typically happens right after your foot hits the ground. And then what's called the active peak during the middle of stance. And when you put a little accelerometer on your shank or on your foot, it's mostly picking up this smacking of the ground, this impact peak. And so the general idea behind these wearable sensor products was, the harder your foot hits the ground, the more force is felt by your body. And as the picture on the right kind of shows in cartoon form, the harder the force, the more force is transmitted up your musculoskeletal system. And therefore, if you're landing with a lot of hard foot strikes, then you may be at elevated risk of tibial stress fractures or other injuries. And as we dug into it, we started saying, well, that's the force on the bottom of your foot, or really the bottom of your shoe. But what about the force that's actually felt by the tibia bone? After all, these overuse injuries are repetitive loading to the bone, in this case, the tibia, your shank bone. And if you look at the force on your tibia bone, it's wildly different. So the forces on your tibia bone are actually somewhere between about 6 to 14 times your body weight, and occurred at a completely different part of the of the running stride during mid stance, not during this impact peak. And that's because the majority of the force that your bones feel it's actually self-inflicted. It's because your muscles are contracting hard to generate torque about your joints. And so this was kind of a key insight for us, was, well, if the force repetitive loading is what's causing or increasing your risk of these stress fractures, then how do we make sure we're estimating something related to this bone loading? And long story short, we ended up going through and doing an experiment where we studied individuals running over different speeds and slopes, and plotted on the y-axis here is our lab-based kind of ground truth estimate of tibial bone loading. And on the x-axis is loading rate. It's one of the key metrics that's used by most of these wearable sensor technologies to quantify how much of impact there is during running. And we found there was really no correlation between these metrics. And that motivated us to say, well, if looking at the impact isn't the way to understand bone loading, is there a better way to accomplish this? And Emily, who was a former grad student of mine who graduated at the end of last year, did some really fantastic work basically combining multiple wearable sensors. So instead of just using a single accelerometer, using a combination of pressure insoles and accelerometers, and using a combination of physics-based modeling and also machine learning to develop some much improved algorithms to better estimate bone loading out in the real world. And so the kind of vision for the future and where this is taking us is trying to develop this both practical and accurate tools. This practical being something low profile, lightweight, that could fit inside your shoe and could still provide relatively accurate estimates of bone loading in the real world. This could be used for research purposes. This could also be used for clinical populations where you're trying to understand, for instance, how much they're loading a tissue either after an injury or after a surgery. So we're in the process of trying to translate some of these algorithms and this wearable sensor system outside the lab. As a quick aside, kind of this general thrust of wearable sensor technology to monitor loading inside the body, to better understand health and injury risk. There's also other applications. So we're exploring how to use these same sorts of systems in occupational health, in the workplace, handling objects, basically material handling, lifting and bending with heavy objects is one of the leading causes of musculoskeletal injuries, one of the leading causes for missed work, for workers' compensation. And so we ended up doing another study where we, again, kind of tried to figure out what's the minimum sensor subset that you could place on someone and use that to monitor how much loading they're putting on their back. And then use that information and feed it into an ergonomics risk assessment tool in order to better understand and manage injury risks in the workplace. So let me kind of come back to the purpose of this. So the lesson really was, for us, a big part of what we do, starting with the biomechanics and the science, is kind of focusing on that science foundation before we go too deep into developing a solution. And I think historically, a lot of folks have developed wearable sensor solutions that have monitored this ground reaction force, this very small blue line at the bottom. But recognizing the etiology, the cause of these bone stress injuries, we're trying to develop tools that get us closer to the source of this injury, and that's really the loading, which is this red line, and what we're estimating now with these combination of pressure insoles and inertial measurement units and machine learning. Okay, all that said, we've been making progress. We're excited about some of the advances and discoveries we've made, but there's always more science to do. There's tons of things we still don't know definitively. These sensor systems we developed, we don't know exactly how the accuracy changes with every different terrain or every running shoe or every sock or every age or every style of running. We don't know exactly the minimum number of pressure insoles we need per shoe or the minimum sampling frequency that will allow us to maximize the battery life of the device. So there's a lot that we still don't know, but I've come to appreciate that the science is going to keep going. We're going to keep doing this research. But I like the quote of, you don't let perfection be the enemy of good. We've reached the point where we're starting to explore how do we translate this technology outside the lab. The slide before this, you could spend an entire career trying to answer all the feasible research questions. But at some point, I've discovered that you need to kind of move towards translation, move towards prototyping, and start to work both the science and the engineering development in tandem. And that actually moves things along a lot further. And once things do get outside the lab, then that opens up new opportunities to gain knowledge that we couldn't reach simply by using our laboratory instrumentation. Okay, so the second lesson for me was just kind of frequently reassessing our questions and our priorities. And this story starts back a few years ago. We started a project on prosthetic feet. And really the idea behind this project was, if you look at most prosthetic feet on the commercial market, in fact, nearly every single prosthetic foot on the commercial market, they generally do not have a toe joint. They generally just have a flat carbon fiber keel that goes through the middle of that prosthetic foot. And based on some of the prior science and some of the literature, we hypothesized that adding a toe joint might be beneficial during certain locomotor tasks. And so we brought in individuals and had them test walking on the same exact prosthetic foot with and without a toe joint. And we were really focused on locomotion and mobility. But in early 2020, we had this individual come into our lab, and you'll see a couple of quotes pop up on the video here. So you can go ahead and read those as I'm kind of talking through things. But he's a carpenter, and as part of his job, he would frequently have to get on the ground in order to do his work. And in this video, he was basically explaining to us how his leg was useless to him. And so he would just literally take it off when he was working on the ground. And then he would take his entire leg off and use it as a crutch to stand up. And this was just really eye-opening to us. I mean, the idea that you have to take your leg off to use it as a crutch to stand up is pretty absurd. And so even though we had largely been focused on locomotion, on walking, on ramps, on stairs, based on input from this gentleman and some other prosthetists and patients, we ended up pivoting our research a bit and really going deep based on user feedback on like what tasks, what activities of daily living were really giving them the most trouble. And some of the ones that came up frequently are things like sit to stand, or the ability to squat down if you have to get laundry out of your washer or dryer, or to lunge forward to get something off of a shelf or a table. And these were often perceived as destabilizing. This individual in this current video is very athletic. And so he was able to compensate with his intact limb and do some of these tasks, but he told us verbally how difficult some of them were. Some other individuals who are not quite as athletic wouldn't be able to do some of the things that you're seeing him do here. And so what we did is we started to learn more about these tasks. He's doing these activities on these blue force plates. And so we were able to also monitor that during some of these tasks, he was putting anywhere from 2 to 9 times more force on his intact, healthy limb than he was on his prosthetic limb. And so we started thinking about the same questions of, can we design the prosthetic limb or features of the prosthesis differently in order to improve his stability or improve the ability of him to do some of these functional activities. And there's an aspect of this research that also involves a robotic ankle, which we're using more as an emulator system to understand what happens if you start adding degrees of freedom or certain behaviors at the ankle as well as at the toe. So kind of the takeaway here was just, even though we started focused really on mobility and locomotion, it was based on just listening and learning from the end users that there were some other tasks that seemed to be of higher priority to them. And that ended up influencing the direction we took the research. And I think that's healthy in what we should be doing, and it can be difficult within the context of maybe a funded grant proposal or a program, but it's been very rewarding for me each time we've made kind of the difficult decision to take a step back from our research to say, even though we have momentum in one direction, we're hearing from stakeholders or end users that this other direction is potentially even more important, and kind of reacting and pivoting based on that new information. And then the last lesson is just to remember humans are sweaty, squishy, quirky, and multifaceted. So a lot of the work we do is on this wearable technology, prosthetic limbs, exoskeletons, exosuits. It's objectively cool tech, and we love it. It's fun to work on. It's interesting. It's fascinating. But I've really gained an appreciation over, I'd say, the last 4 years on just how important some of these other factors are if you want to try to take some of these concepts, these early prototypes, and translate them outside the lab. Um, I see these pictures of Tony Stark, and I love Marvel and Iron Man and all these movies, but there is an absurd amount of metal next to this man's skin, and I just find it very difficult to believe that this is a comfortable suit to wear. And in reality, if you're designing technologies and trying to get them to people who can benefit in real life, they're going to care about that type of physical comfort. Iron Man is basically just a guy in a big metal box. I assume that probably gets warm from time to time. That is going to be a problem if you're trying to translate that outside the lab. So thermal comfort has been one of the big challenges across the exoskeleton industry in terms of how do you create devices that are sufficiently cool that people will tolerate wearing them for prolonged periods of time. You can't neglect the female body. This has been a problem in personal protective equipment long before exoskeletons were on the radar. But certainly for exoskeletons, there is a challenge right now, and historically there has been a problem where there's many devices that are designed to fit the male body better than they fit the female body. And this is something that as a field of folks working in exoskeletons or wearable assistive technologies that we need to address head on and not go down the same path of failing to account for or design for the female body. Soft tissues, when you design and you're attaching your cool tech to a person, it's got to apply forces somewhere. I like this video of a guy getting hit in the face with a soccer ball just to show all of the soft tissue vibration and motion that occurs. And this type of thing is happening wherever you're attaching to the body and applying forces. A few years ago, we did a scientific study on this where we instrumented different parts of a person's body and different parts of a device and looked at when you actually apply a force and try to transmit mechanical power from the device to the person, there is deformation of the soft tissues, there's deformation or stretching of the interface materials themselves, and it actually affects how power is transferred from the device to the person. And so that's just an interesting aspect of the design, is really thinking about how to design the robot in order to be effective in transmitting forces, given that they have to go through some amount of soft tissue. And then in designing a lot of these technologies, just not losing track of the big picture. This is an individual that works in a warehouse. He does a lot of palletizing or depalletizing work. And oftentimes, in the research lab or in the research world, we talk about designing technologies to help reduce back strain or reduce risks of back injury to individuals such as this. And certainly this individual is bending and lifting hundreds of times an hour and would love assistance, would love relief. But you can see from this video, which is at 10 times speed of what he's actually working at, but he does a whole lot more than just lift. And so if you're designing a solution, it has to be able to keep up with his daily job. It can't interfere with other tasks or other important aspects of his work. So, over the last few years, we continue to be interested in device design, but some of the work we've done, which has been most insightful, has really been trying to key in on some of these specific challenges. And so, for instance, even before designing a device, one of the things we did was attach a robot to different segments of the body, and we pulled on people first gently and then harder and harder and harder until they basically told us to stop, until we reached their comfort limit. And by understanding how hard we could push or pull on different parts of the body, that helped us build out, in a sense, design requirements. Like, what would it be feasible for a device to do to assist a person? And so understanding this interface, understanding some of these subjective comfort principles has actually been really integral to designing effective devices. Looking at the big picture and trying to understand, what we call user stories or user experience. So again, a warehouse worker who might do 150 lifts per hour every time they bend over and lift something, so they lift something off the racks onto their pallet, it might take 2.5 seconds. But you can just work through and do the math. Even though these are very lifting intensive jobs, very physically demanding jobs, they're only lifting 10% of the time, and 90% of the time they're doing something else. And so this type of information has really, guided my philosophy or my approach to designing at least occupational exosuits, which is, even though we think of these as wearable assistance devices, the number one goal, the thing that an exoskeleton or exosuit needs to do most of the time, is just stay the hell out of the way. That's what it needs to be good at. And then secondarily, occasionally it needs to be able to assist or provide support. And so this is really kind of the philosophy that I've the philosophy that I've embraced. It started in my research lab, and it's been carried over to our spin-off company, Heroware, which created this back assist exosuit, really with this belief that first and foremost, it has to be light and comfortable and stay out of the way and fit all the different aspects of somebody's job. And if you're working in construction or you're working in logistics or agriculture, you do a lot more than just bending and lifting, and we have to be able to accommodate that. Okay, so I mentioned the term quirky in the title, and just wanted to circle back to address that. So I actually mean quirky in a very good way, which is just that anytime you give somebody a tool, people are very clever and they figure out unexpected or interesting ways to use it. This is an example of a construction worker who, we initially provided this exosuit because he does a lot of lifting and bending within the context of construction. But some of the things he told us after he started using the device, like, oh, because I'm able to rely on the suit, I don't have to lean on my knee as much. And when I don't have to lean on my knee doesn't hurt as much from this heavy saw. And so it's really interesting to see, once these devices get out there and people start using them, there's some unexpected and often interesting benefits or ways to use the devices. And the same goes for me. I use exosuits on the weekend around the house for gardening or home improvement stuff. I've been known to play Frisbee or other things with my kids while wearing exosuits, but it just gives you a different appreciation for what's possible. Very proud of myself for making a diving Frisbee catch and not hurting myself. But again, quirky to me is just, people being clever, them finding new ways to use tools, whether it's a wearable device or anything else. And I think that's been a really rewarding and interesting aspect of translating some of these technologies outside the lab. I also just say that the workers themselves often come back and provide some of the feedback that help you understand how people are using a new technology. These are quotes from workers that have been using these exosuits day in and day out for weeks. One of them mentioned that with the device, it actually helped him pick up boxes off of a pallet with better form. So even though the device was primarily designed to route some of the forces through the exosuit rather than through the back muscle, so it was really meant to offload the back, some individuals are also reporting that it's helping them maintain better lifting form. And there's been a number of other quotes and feedback that just get us excited about the possibility of these devices really having a positive influence on society and an impact on people's lives. One quick self-reflection is just, I think a mistake I made earlier in my career was, although I was very focused on maybe the technical design requirements when I was, when our team was working on engineering projects, having user stories involved, meaning really thinking through what would a user say, what would be important to them, would they use a device like this, or what would they be concerned about, whether it's in the function of the device, the size of the device, the thermal comfort of the device. That's been really, really beneficial. And in the last few years, we've done a lot more trying to integrate those kind of subjective user stories early in the research and design process. So with that, I'll just circle back to the main takeaways from the talk, which are interdisciplinary proximity and facilities have been very helpful to us in the research we do in this rehabilitation, engineering, and assistive technology space. Beware of too little or too much science. Frequently reassess your questions and your priorities. And then if you find yourself designing for humans, just remember they're sweaty and squishy and quirky and multifaceted. So with that, I'm happy to end here and take any questions, whether it's about the research or anything off topic, whether that's social media for scientists or science communication or whatever you all have on your mind. Happy to chat.
Now feel free to unmute yourselves and ask a question, or you're welcome to put it in the chat. We did have a question early on, Dr. Zelik, from one of our professors, and then a student expanded on it. And she asks, what incentives are there for undergraduate students at UTC to continue their grad work in your program? And then the student adds, where can we look for further information on opportunities?
Yeah, great question. And in terms of our program, I think, the early part of our talk hopefully gave you a sense for kind of how we approach research, how we approach trying to create an environment that's interdisciplinary and provides opportunities for engineers to enhance and develop their research and design skills, but also to connect with patients and clinicians. Choosing a graduate program is I think, a very personal choice. And I think you have to look for places where maybe the research aligns well, the personnel that are there, whether it's the professors or other students, have a similar mindset or style, and somewhere where you feel like you'd be supported and where you could excel. We try our best to create that environment. And so I'm of course biased, but we do the best we can to try to create an inclusive space where people can be successful and maximize their own personal potential along whatever trajectory they're on. In terms of looking for more information, if you're specifically interested in this kind of space of biomechanics or assistive technology, I see a lot of things on Twitter these days. I feel like the biomechanics community has kind of shifted there. There's also a biomechanics listserv called Biomechel, or just talking to your other professors or looking around online, trying to find what research, what universities are doing research that appeals to you.
A question just came in the chat. How do you know what to provide for the customers versus the clients? And I'm thinking,
whoever asked the question, could they maybe define customer versus client? Or anyone else is welcome to chime in. You can say it verbally as well. You don't have to do it in the chat.
They could mean end users versus the companies, maybe that would buy the technology to sell it.
I see. Okay. So yeah, in that sense, and there certainly are. It really depends on the product. So for instance, in prosthetics, that's a great example where the end user is the individual with limb loss, but in general, the customer is the insurance company that's paying for the limb. And so I think if you're interested in translation, even if you are 100% interested in, I just want to improve people's lives, all I want to do is help that end user. The truth is, if you really want to reach that end user, you have to understand the economics, the business, the financial side as well, in order to make sure whatever you're developing will be paid for by the insurance company, so the person you want to help will be able to use it. And in the occupational exoskeleton space or wearable sensor space, it's very similar. Is you might, in some cases, the customer, the person paying, and the end user might be the same person. In some cases, it's the organization, the business is paying for a device in order to support their workers. And it's really the same situation. You just have to understand that ecosystem. You have to understand what's important to each of the stakeholders, and basically understand how to deliver what each of them needs in order to successfully have the impact you want to have.
And the person that asked that question said thank you. So
okay. I guess I answered the right one then.
Hi, Dr. Karl. I have a question.
Go for it.
When do you think your exosuit will be brought to market?
Our exosuit, it launched in March of 2020. So it is out on the market. I think right now we've got clients in over 30 states and 12 countries. I think just in the last couple months, we've gone live in more than a couple dozen sites. So it's yeah, we've made the transition from university prototype and research to independent company that is has a product and is selling and growing and expanding.
How many products does your company have patents for?
So on Heroware side, I saw somebody throw up a 5. So Heroware as an early stage company has one product. It's the Apex exosuit, and from the Heroware perspective is really focused on delivering a high quality product and getting market fit and kind of scaling that up. And then there'll be additional follow-on products in the future.
Okay, thank you.
Sure.
We had a question come through the chat from Dr. Nassab. How time consuming is the FDA approval for such devices?
So it all depends on the device. I'm trying to think. I personally have not gone through the FDA approval process, so I don't want to say too much about this because my knowledge of it is secondhand. Michael Goldfarb, who I work with, has gone through that with his Indigo exoskeleton, and it was definitely years of work running some clinical trials, and a lot of that work, once it gets into the clinical trial phase, is done by clinicians or clinical researchers. So it wasn't necessarily all on him to complete, but it was a considerable amount of effort to get through the FDA process. And then even if you're through the FDA process for some of these medical devices, oftentimes the really big challenge is still you need to get insurance companies to pay for the device. And that's a whole nother process and challenge to get through. For devices like the Occupational Exosuit that Heroware makes, it's not a device that is treating a disorder. It's not a therapeutic device. So it's actually not an FDA approved device. It's not something that would go through FDA approval because FDA approval only covers the devices that have those kind of medical claims. If it's an assistive device or something that's meant for prevention, then there are other standards or certifications in place, but it's not an FDA approval process.
There's a question in the chat. Are the parameters on the EXO modifiable depending on the task or learning that happened in the subject after using it for a while?
Reading this one, are the parameters on the EXO modifiable? Is this a general question about exoskeletons, or was there a specific device in mind? Is this the Indigo exoskeleton for people who are paralyzed, or an occupational wearable? I guess I'll answer the general question, which is there are some exoskeletons where they need to be tuned. There's parameters that either upon fitting and training need to be tuned for that individual, or if it's a device that's being used to rehabilitate someone over time, those parameters may change over time. In other words, you might want to assist somebody a lot at the beginning and then start weaning them off the assistance as they're getting better. So there are certainly certain classes of devices where parameters are going to be modifiable and tuned. And then there's going to be other sets of devices where it's closer to the answer of no. You basically figure out what setting works for you and you go on your way. That said, a lot of devices still have some amount of adjustability, either swappable springs or settings that you can change. So it really runs that gambit, and it depends on the specific device, the specific application, and end user as to whether you would continually adjust parameters.
Okay, we're at almost the end of our time, but is there maybe another question out there?
Yeah, I have one question.
Go for it.
So yeah, thank you for your great presentation. I'm very happy to see some familiar faces, which I saw before. So yeah, before the COVID, as you remember that we tried to start collaboration between your lab and my lab in UTC. I hope we'll continue after COVID. So my question is there any another advantage of your product, I mean, Hero Apex, with the other big companies, exosuits, besides lightweight?
What was the question was, are there benefits?
No, is there any other advantage of your product? I mean, Hero Apex, with the compared to another company's exosuits. I know yours very light, so it's big advantage if you compare with the others. So is there any another advantage?
Yeah, I can talk a little bit about that. You know, the things that I think are most exciting about that exosuit. So one is certainly that it's lightweight, so that helps if you're going to be wearing something all day. When we approached it, I said our philosophy was you really have to stay out of people's way, and so designing something that was that did not interfere, that allowed people to have full freedom of movement, is something we're really proud of, and our device does a great job of, and that's been a big obstacle for a lot of the other exoskeletons. Two other things, or maybe two or three other things. One is there's actually a little switch on the shoulder. So if you want the assistance on, you just press the button, and then anytime you bend over, some of the strain goes through the suit. If you need to climb a ladder or hop in a forklift or do anything else, you just press the button again, and you have full freedom of motion. It basically decouples the spring. So that's one of the kind of patent pending aspects of the design that we think makes it really functional. One other thing that I'll draw attention to that I'm really proud of is we're the first company to release a first exoskeleton or exosuit company to release a female version of the device. In other words, it has actually straps that are designed specifically for females that curve in a way that go around the breast to fit more comfortably. And I mentioned that in the talk as well, that, you know, designing for the female body has been a big challenge. So the combination of the modularity and lightweight and freedom of movement, I feel like we found kind of a sweet spot where people are able to benefit from the device, but it minimizes the again any interference or comfort issues that have been a big challenge with the occupational exoskeleton field.
No, thank you.
All right, well, thank you so much, Dr. Zelik, for the talk today. We really appreciate it. Appreciate you sharing your knowledge and time. And a comment in the chat, thank you for including design for the female body. So we appreciate it. Thank you for the wonderful presentation. And we'll have this recorded in case you missed any of it. Just everybody on here, watch your email, check the CECS website. And thank you so much again for your time, Dr. Zelik. We appreciate it.
Yeah, thanks for having me. Take care.